The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI Conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content. You can earn continuing education credits through ACI's online CEU program. Visit www.concrete.org to register. ACI Conventions provide an opportunity for networking and for keeping up to date with the latest in concrete technology and practices. This is one of 3 ACI web sessions covering the 2010 Fall Convention session entitled Sustainability of Concrete Pavement. This session includes audio and presentations for 2 speakers. Please enjoy the presentations.
Our next speaker, John Kevern. He's the assistant professor at the University of Missouri, Kansas City, and he's going to be talking about green streets. John?
I teach a green building sustainable infrastructure course, and Lionel mentioned that, it's kind of a low standard to achieve the highest rating. The first time we went over green roads in there, the whole class lobbied that a 59% should be an A after that. So it is, if you think about it, it's a little bit low. We've had some real good speakers this morning talking about initiatives, talking about ideas, and so kind of change it up a little bit. I've collected a bunch of case studies, some things that are actually on the ground, so we can show you pictures, show you what's been done, or what do these things actually look like when we put them down. So I have to acknowledge Leif Hasselbeck at Washington State is co-author on this one, and anything you don't like in here came from her. So what is a green street? In the Pacific Northwest, the specific definition of a green street is aimed towards stormwater management. But really, if we're kind of talking about big picture sustainability, Green Street allows equity access for all our users, balances our environmental impacts with the materials we use, and then the impacts of that throughout the whole life cycle. So like Leif mentioned, we've got to think about the initial materials that go into that, but we also, the design of that, a poorly designed street, even if it's got 100% recycled materials, isn't a green street. So we have to think about the whole big picture when we do these. So little things I'll touch on here. We got pedestrian access, alternative transportation, integrated design, materials, stormwater, urban heat island, light pollution, emissions, and then we've got kind of this education. And so we've got, some of our hard side stuff that the engineers really love, and then we've got all this kind of the soft, squishy stuff that the urban planning people love to talk about, but it's real hard to quantify. But that's kind of in that big use phase. So we put this together, and then Leif said, wait, this is a concrete session, so see how all the concrete we can use in here, all these pictures. So improving access. Here's, this is the city of Chicago. We say we want people to be outside more. We want them to walk around. We want them to use sidewalks. We want them to use bus stops, ADA compliance. And then we look at this and say, that could be all recycled material. You still don't want to be out there on that street. You don't feel safe. It doesn't look good. You don't want to stand there and use the bus stop. So we've got to have, it's got to be safer for the people. It's got to be better looking. Safer walking surfaces. I've been doing quite a bit of biomechanics work with pervious concrete and different pavement surfaces, and this is a number one concern for elderly people. And as the population ages, they are very conscious of their local, the surface texture of their local pharmacy, their local grocery store. If they perceive it as a slippery surface or an unsafe surface, they do not go there. They'll drive farther across town to go to where they think it's safer or brighter or things like that. And some of these people you don't want driving farther to try to go to what they think is a safer surface. So I'm a civil engineer and I've got a biomechanics grad student right now, but we're looking at the biomechanics of walking on frozen pavements, wet, icy pavements, and it turns out we know that the snow and the ice and the water go through pervious pretty well, but it's also, it turns out we can quantify that it is a much safer walking surface. It melts off quicker, it's got a higher coefficient of friction on that initial slip, and it turns out these are safer pavements. So things that are hard to quantify, but to consider as well. Alternative transportation, relocating bus stops, making bus stops ADA compliant. I waited a bus stop like this yesterday that's kind of in the not the greatest areas. So if we want to increase the use of alternative transportation, you have to invite people to want to use the alternative transportation. Improving access to alternative transportation. So here's Cleveland. We've got clearly marked bike lanes. You go to Boise, Idaho. All new subdivisions in Boise have bike lanes that do not cross roadways. So if you want to ride to the center of town from 3-4 miles away, no problem. You're not crossing roads. You don't have any stoplights. If your children want to ride to school, you're not worried about them crossing traffic. That's a very nice place to live. If you feel like you can ride your bike, you might ride your bike more. All right, alternative transportation. What's this funky thing on the left? This is in Brazil. And I will verify from riding the bus yesterday, what's one of the biggest concerns of riding the bus or complaints is people getting onto the bus. If you have a hard time making that step up, it takes a long time to get people onto the bus. So the bus takes longer, gets off its schedule. You don't want to ride the bus. So what they've done here is this is just a little covered pod that you get up to the height of the bus, pulls up, and then you come in at the same level. Makes it move a little bit faster. And then we pulled this from the City of Chicago's webpage, but this is kind of integrating design here. So we've got light-colored, permeable sidewalks, and we've got some integrated stormwater designs, and we've got some permeable pavements or optimized pavement designs there, and then we've got optimized bus lanes. So let's draw all these things together. So material improvements, we use industrial byproducts and recycle wash water and aggregates and all the good stuff that we've been talking about here. Better choices, again, two-lift pavements that Tom showed. If you've got same performance, more recycled materials, lower CO2, lower cost, it's kind of a smart idea. Managing stormwater. Green Streets, Pacific Northwest, this is what comes to mind. So we've got, originally, before we were all here, it was great, and the rain fell, and it soaked in, and everything was perfect, and then we put our streets in and ruined it. But streets do a lot of good for us, too. But the idea is we want to get some more water back into the ground. Do that by mimicking our former site hydrology, so do that by storing some water on site instead of letting it run off really fast. Let it infiltrate into the groundwater, let it evaporate, let it uptake in plants, and let it get detained. So if you look at this presentation, I've got some pretty decent references on there. If you're looking for low-impact design manuals that are available, City of Seattle's got their right-of-way manual. Portland has a stormwater manual that's real good. And so there's links that pop through here that if you see some of these pictures and you say, where'd that come from? I'd like that design. Go on the web page, pull it up. They've got some fairly developed designs that you can apply anywhere. So here's an example. We took a curb cutout, put it in Kansas City. Works just fine with all the salt and crud and everything that runs down the street, even in Kansas City. So if we're talking about Green Street, the stormwater technologies for Green Streets, really kind of looking at three major ideas here. So we've got curb extensions, where we just take our curb, bump it out. We can dig down into the pavement, or we can do it on the surface there. We can do our permeable pavements, and then do stormwater planters. Actually, the water goes in, they're detained. Some evaporates, but we're going to clean it as well. Okay. Biotreatment, Pacific Northwest. They are farther advanced than most everybody else, but really started in the late 90s. Bioretention BMPs are now their preferred means of control in the street arena. Portland's got it since 2008, and we've got City of Portland has 2,000 plus flow-through stormwater planters. So this is a pretty widespread technology here. Water comes in, here's a curb cut, we've got our plantings in there, some check dams, water flows through, and then whatever is clean, slowed down, and goes out the other side. This was 2006 American Landscape Architect of the Year winning award. This is Siskiyou Street curb extension. We've got a residential area, need to treat stormwater, don't have any place to put a traditional detention pond. So what did, take 2 stalls, water's running down the curb line, and put these curb extensions on there to manage the stormwater. Helps with the stormwater volume, helps with the rate coming off there, helps some cleaning. They do like this. It's traffic calming, so you are now funneling traffic there. You're only dealing with 1 car each direction, so it's helping with some pedestrian safety with pedestrians crossing right there. So here's a close-up. Got plantings, again, cut in there. We've got a couple check dams and some plantings in there. So what's this thing look like? Here's a picture of check dams. We've got our topsoil, compacted clay, water comes in, got some dams. So if you look, here's a City of Portland Stormwater Manual. If you're worried about check dams, we actually have a check dam spacing guide. So there are some, I'd say, very developed design guides out there for putting these things in. So if it looks good, it looks great. But other things to think about, I mean, we're now taking a green construction and we're putting it in our downtown area. We're putting in a heavy urban area, and there are some additional considerations to think about. Our bioinfiltration, so the media we put down has some sort of design infiltration rate. Same thing with pervious concrete. If we put it in, it's got a good infiltration rate, and then we don't protect it from construction run-on of soil, we plug the whole thing up. It happens with pervious all the time. It can happen with stormwater planters. You can't let all the crud come in there before it's completely built. Compaction should be avoided. Normally we compact our soil, but that is completely contrary to getting water in the ground. So for these things, if we're trying to get water in the ground, we have to watch the level of compaction in the soil. Typically, we'll put our media or pervious concrete or whatever in as the final component. And a lot of times we'll block these out so we don't get all this construction crud coming in and plugging it up first thing. Inspection and maintenance. Same with lots of different BMPs, but these do have to be inspected, do have to be maintained. They're not natural systems. They're supposed to mimic, so we have to clean out some of the trash every now and then. We've mentioned a couple times pervious concrete. This is we're taking our detention pond, put it underneath our pavement. And the top surface, the pervious surface, is just a mechanism to get the water through the pavement rather quickly so it can back up and infiltrate into the ground. What about designs? We've got Seattle Right-of-Way Manual, Portland Stormwater Manual. We've got thickness design. We've got engineer requirements. These things are available online. If you need to go get the specifications, they are available. Again, this is the Low Impact Development Design Manual for Highway Runoff Control. This is Washington State, but we've got different BMPs that are available, operations, permeable pavements, bioretention in there, but what they treat, where to go for the design. So these are available right now. Urban heat islands, talked about this, are dark impervious surfaces, absorb more energy. During the daytime, get hotter. They don't evaporate water. We get higher overall temperature. We have health problems. We've got higher energy demand. We're just all these kind of bad things. Traditionally, what we kind of think with urban heat islands is we have the downtown area is real hot. We have a whole bunch of CO2 generation, excess heat generation in the downtown area. If we're looking at CO2s are kind of the easy greenhouse gas to look at. But normally, or what we're thinking now, if we're looking at just the households here on the left, if you live in a city, you've got a relatively small footprint, maybe don't have a car, maybe 1 car per household. But if you live in the outskirts, generate more CO2 per household. So we are looking at these green streets, but also, I'd say, pushing it out into the suburbs as well. So urban heat island strategies, highly reflective cool surfaces, We've got infrared blocking coatings we can spray on so they don't absorb so much heat. Permeable pavements, we shade it or we put vegetation in good. So if we look at pervious concrete, we kind of get this heating phenomena similar to sand at the beach where the surface gets really hot, but if you go under the surface, it's nice and cool. It's a poorly connected pavement, so it's hard to get the heat to transmit real deep into the pavement, so it stores less heat overall. Energy efficient lighting, if you've got brighter pavements, you can space your lighting out farther. Chicago's done a couple tests, and they've had some I'd say a lot of success with using white light, low energy lighting, and spacing them farther apart. Construction emissions. If we use more durable materials, we're rebuilding it less, maintaining it less, we save construction emissions, but then also using more efficient construction equipment. And this is part of the Green Roads advocates using the EPA Tier 4 emission standards on the construction equipment. Here's an example. We take an underground mine tour with the students. They don't use electric. They don't use whatever non-emitting construction equipment. They use the regular EPA Tier 4 diesel construction equipment down in the mine. You stand next to those, they're not belching out black fumes. You can't hardly smell what's going on. We do have these technologies available. And then public education. So it all works great, but if the public is still pouring antifreeze down the drain, we've kind of missed the whole point here. So talk about car washing, talk about how to properly throw away chemicals, how to properly apply fertilizers, monitor soil erosion, and then littering and pet waste are also big areas of public education. Couple case studies. Austin's got a Grow Green process or a program where they're optimizing or trying to help you optimize your fertilizer and then trying to pick up pet waste. And they both, we reduced 135,000 pounds of pet waste. This normally goes into the stormwater. We can have a little bit of education, some really big improvements. And then regional materials, Living Building Challenge. LEED uses 500 miles. Some of the different rating systems use lower miles for heavier materials. So what's a green street? Trying to look at everything at the same time. So for more information, here's some real good stormwater management design manuals on there. So,
well, thank you very much, John. Okay, our last presentation today is John Ries. He's the president of Expanded Shale, Clay, and Slate Institute. And his presentation is 100-year concrete pavement service life using internal curing.
Thank you. First, I want to ask you a couple questions. How many in this room believe we can economically build 100-year concrete pavements? Raise your hand. Super, thank you. And how many of you think we should try? Good. I'm speaking with a great audience here. Thank you very much. Yes, we got them sold. That's great. Okay, sustainability. What is it? Well, it's all about time. Is 100-year pavement life sustainability? You just ask the FHWA people and you ask the DOT people, they're going to tell you yes. They want it to last longer. I say it's just good design and common sense. So, sustainability is a decision. It's a shift in attitudes. So to solve this whole sustainability issue, I'd say all we have is an attitude problem. We just need to shift our attitudes. And it's a design issue. Here's a great example of the engineers knew about sustainability. The political and the economic part of that industry did not, and the Roman Empire collapsed. The reason I point this out to you, see this dome on top? This dome is lightweight concrete. It's been around a long time. Now, you might say, well, there's no trucks driving up there. There's no free saw up there. Well, take a look at this. This is a concrete ship built 90 years ago, 100% lightweight. The hull of this ship was only 4.5 inches thick to 5.5 inches thick. 100% lightweight concrete. And here's its sister ship that was built the year after that one. It's still floating today. Now, it looks a little banged up, but if you were out in seawater and freezing and banging around and all kinds of stuff on the surface, you might look a little banged up too, but it's still floating. And we went out there 10 years ago, and we core drilled it. Well, CTL core drilled it. This is in the splash zone, so take a look at this. There's only 3/4 of an inch of cover over that steel. This concrete was in absolutely perfect condition. CTL wrote a big report about it, and they said it was a pleasure to look at concrete that was in perfect condition. No air entrainment, folks. 0 air entrainment. So there's something special going on with this lightweight aggregate, and what is it? What we're talking about is a material that's half the weight of sand and stone and gravel and dirt. So what's going on with this stuff? Well, it's internal curing. It's a unique process that just happens naturally. So the use of internal curing, I call, is a common sense addition to the sustainability of concrete. Now, it's not new. We've been doing this since the 1950s. We called it self-curing. We called it lightweight concrete. It's very forgiving. In the field, they abuse our product. They abuse lightweight concrete. They abuse it bad. They pump it up there at 10-inch slumps, and it always performs. Here's the basics of internal curing. The one on the left is just a regular Portland cement mix, or it could be fly ash. When it hydrates, as you can see, all this water in here, it creates a void. In other words, it's starving for water. Well, you add lightweight aggregate to that same mix, and the lightweight aggregate has absorbed water in it. Well, it pulls the absorbed water out of these larger pores, sucks it into the cement paste, and therefore you always have 100% moisture needed for the hydration of the cement. So what is internal curing? Well, here's the ACI definition. I'm not going to read that for you, but they add pre-wetted lightweight aggregate, and it's to help hydration, and it eliminates self-desiccation. This is a big thing. And they predominantly use fine aggregate. Fines are intermediates, and they don't use a lot. It's maybe 300 to 400 pounds, 5 to 7 cubic feet per mix. And it's especially helpful for high-performance concretes and stuff with a lot of low water cement ratios and supplementary cementitious materials. But it's beneficial for all concrete. So internal curing, here's a great study done down in Chile by Dr. Lopez. I don't know if he's in the room, but he's running around out here. They did 10 concretes, water cement ratios going from 0.4 to 0.5. So these are not high-performance mixes. These are day-to-day mixes. They dried these things at 24 hours. They let them set at room temperature and at 50% relative humidity, and this is what they found. Now, this is pretty impressive. 16% increase better hydration, 19% higher compressive strength, 30% lower permeability, and internal curing was very useful for poorly cured concrete. Now, where can you get poorly cured concrete very quickly? On pavements, on surfaces, a lot of evaporation. Purdue came up the same thing. Look at their water cement ratios went up here. The internal curing one definitely had better hydration than the one without internal curing. So it's not just coming from one source. So we designed for intended service life. So pavement's durability is about crack control. And it starts with the microstructure, the micro cracks. And the micro cracks usually happen right around the aggregates or in the plastic shrinkage and whatnot. So reducing the micro cracks improves durability, improves longevity, improves service life. So structural lightweight aggregate is about controlling cracks. Well, we're against crack. We're against crack houses. We're against all kinds of cracks. Cracks in concrete. So if you remember anything, just remember we're against cracks. Now, also we improved the bond of the aggregate. So this is a lightweight aggregate. You see, look at the rough surface texture on this thing. Look at the voids inside the aggregate. And there's a strong mechanical bond because of that rough microsurface texture. And there's also an improved chemical bond. And that chemical bond, because the surfaces of these aggregates are slightly pozzolanic. And that reduces the microstructure, the microcracking. So you take a look at this. Here's a great example. This is a lightweight aggregate. Here's the cement. You can see this bond between them. Here you get a closer look. They're almost welded together. And in contrast, you look at here. Here's an aggregate particle, normal weight. And here's the calcium hydroxide, the cement. And almost always you're going to find a clear demarcation or a clear, sometimes even a micro crack at these surfaces. Now this is a little bit complicated, but not that complicated. The one on the right, this whole half is normal weight concrete. This whole half over here is lightweight concrete. And the top half is when it's fresh concrete, and the bottom half is when it's hardened concrete. Well, if you look up in the right corner, what you're seeing up here is this is a normal dense concrete. The water comes to it, and it builds a waterlands on the aggregate. And then you get this transition zone afterwards. It's not that big, but some cases, if you add silica fumes and whatnot, it makes this transition zone a lot better. Now, in contrast, over here with the lightweight aggregate, you don't get that water lens. Somehow, because of the porosity of the aggregate and everything, you get a more of an equilibrium effect. And then as soon as it starts hardening, this moisture comes out of the aggregate and comes in here, and you get a lot better, what we call a contact zone. And here's a better demonstration. Or here's just an absorption thing. This is just an aggregate. Now, the phrase, we use pre-wetted all the time. We don't use saturated because you can never really saturate a lightweight aggregate particle. Some of this stuff internally here will never fully saturate. And you get pretty good saturation, pretty good absorption, I should say, depending on the aggregate. Up to about 24 hours, it takes on water very quickly. And after that, it takes it on much slower. And then eventually, it will fully saturate. Now, here we go. Look at this. Lightweight aggregate, as it comes out, the water comes out. It comes out about 2 millimeters. It comes into the paste. And this is the transition zone where you get the internal curing. Now, as it comes out, this curve shows you the desorption curve. And the blue line shows you aggregates that give you a lot better internal curing than the red line. Now, what you want is you want the moisture to come out with a relatively high humidity inside it. And so about up to 90%, you want this moisture to be coming out because that's when the cement really needs it. The cement or the supplementary cementitious materials. So why use internal curing? Well, it mitigates autogenous shrinkage. It minimizes plastic shrinkage cracking. It reduces crack width and can even eliminate cracks. It delays drying shrinkage. It mitigates self-desiccation. It mitigates micro cracks. And it disconnects the capillaries, and it reduces the chloride intrusion, and it gains strength. Now, all I can say is, wow. I mean, that is a home run if there ever was one in sustainability, and you can get it almost free. It's just water that's in the aggregate. It's been around a long time. And it helps offset poor curing. Now, here's some great stuff from Purdue. What you're seeing here is they add the lightweight aggregate for the internal curing. And these vertical lines are where it cracked. This is unrestrained shrinkage. And you can see it's cracking here at 6 hours, or 6 days, and then it adds up. Well, you start getting up this 14%, these things do not crack. And this top one, these two do not crack. And that's the same here with unrestrained shrinkage. As you can see, when you get up to this 14%, these things, they're not shrinking. And they'll go on forever. And so there's the benefit of using this internal curing. Some of these slides I stole from these great professors. This is out of Auburn. The same concept here. You know, at 48 hours, or at less than 40 hours, the normal weight concrete was cracking and the internal curing was. Here they went out with structural lightweight concrete, which were like all the coarse aggregate, all the fine aggregate, and here's all lightweight. They had to get these to crack. They had to change the temperature of the cracking machine and force it to crack. And the same was at 95 degrees at a higher temperature. It obviously cracked quicker. And the gentleman that did all of this research, he's sitting here in the room, and he might jump up later and tell you all about it. But this is the preliminary stuff, and they're just getting ready to publish their major report, to understand. Now look at the benefits here. These are life cycle models. This is normal weight, high-performance concrete. You get 40 years. You jumped 18 years from here to here. Just taking that same high-performance mix, adding internal curing, you jumped an additional 23 years. That's staggering. Here's the cost of these, initial cost. Okay, the high-performance mix was 25% more, and you added 18 years. The internal curing one, the cost was 29% more than the original, or 4% more than this high-performance, and you added an additional 23. You look at the present value of this thing, look at here, the benefit is unbelievable. 63% reduction just by adding internal curing. Now, these costs translate very closely to CO2 emissions and carbon footprint. Cost, not exactly, but there's a definite trend. So what you're seeing is a major reduction in the carbon footprint by adding extended life onto the pavement. Now, granted, we're only at 63 years here, but we're definitely pointed in the direction. There's a lot of other things you can do to concrete. Internal curing just helps those things. Judy Buffenberger talked about all kinds of great things you can add to concrete. Okay, chloride diffusion. Michael Thomas talked about this in the bottom line here at 3 years, 1/3 to 1/2 of the chloride diffusion coefficient by using lightweight concrete. And the M factor is also improved. The M factor is used in Life 365. And now this study was done just basic on the consideration of chloride diffusion only, but it definitely points in the direction of improving it. Now here's a real world situation. This deck has been in for 23 years. It was removed because of the Olympics, and they needed a lot more traffic out there in Salt Lake City. But this is salted very heavily, and you can see at that first line, the chloride penetration was a lot more for the lightweight, but at the second half inch, it was equal. And in the second half inch after that, the third half inch, the lightweight was half. And then it got very low, and why they didn't have one for the normal weight, I don't know. But you can see in the real world, this really does shut down the chloride intrusion. Now here's some case studies, Mainline Paving out of Texas. This is 5 miles, continuous reinforced concrete. They did it in November 2006. And here's their strengths at 78 days. Why I point this out is they're only putting in 5 cubic feet, about 300 pounds, and it's an intermediate grade. It goes from about 3/8, 100% passing to 3/8, down to just only 4% passing to number 16. And so it doesn't have to be fines. Well, we use intermediate. It's a lower grade. I mean, it's a lower sizing that we use. And here it is in real life going down. And as you can see, the shrinkage averaged about, the normal weight was the pink one, and the lightweight was the blue one. And you can see it's averaged at about 10 or 15% total less strain. They also did a crack survey of this particular section. They pulled out a 500-foot section. And at 76 hours, some of the, Victor, I believe, is a room, and a few other people went out and did this whole thing. They found 31, the crack spacings were 31 feet. The DOT says their normal crack spacings are about 5. These are these real micro hairline cracks at about 3 to 5 feet. So they instantly noticed it, a difference. And then when they went out again 10 months later, they found 21 cracks in the light internal cured one and 52 cracks in the normal weight one. And here's what they did. Of the 21 cracks, 90% of them were less than this number, and the control had a lot, but look at over here. Of the cracks, the larger cracks, the control had a much larger percentage of larger cracks. And this is pointed out again here at Purdue. As you can see, as they get up this 18% of the lightweight, you get 0 cracks at all. And as you get down, you start getting less cracks. And the one without any, you get a lot more potential for cracking. Now here's some real life, some big slabs they've done there at Purdue, big test sections, and you can see they fill these with concrete. And here's what's at 12 days, they got a 0.6 millimeters crack width, and over here at 43 days, so almost 4 times as long, they only got a 0.4 crack. And so this internal curing really shuts down the cracks. Here's probably the largest project. This is also done in Texas, in Hutchinson, Texas, 250,000 yards. And at 6 months, I think they might have been drinking or smoking something. They only found 1 crack in this whole thing. But anyway, they went out and looked, and they looked hard. But they came back 5.5 years later, and they did an extensive review. They had like 5 or 6 people running this whole job, looking for hours for cracks. And what they came out was the plastic and drying shrinkage cracks were minuscule. I thought that was pretty impressive. Now, the workability is also great. See, I mean, they love it with these internal curing. They perform the same way right behind the pavers. But since 2003, in Texas, they've done over 2 million cubic yards of internal curing mixes. And these are low slump. About 1.3 million have been low slump on pavements. And most of these are on city streets. And they're using either the 3/8 by 10, which I showed you that example, or they're using a 3/8 by 0. And probably the bulk of the work is being done with outside of Texas is probably the finer gradation, the 3/8 by 0. And I don't claim to be the expert. They say I'm a philosopher with a concrete degree. But this is what they're saying down there. And this is what the people in Texas are going to tell you. They say mitigation, they mitigate or eliminate of plastic and drying shrinkage. That's why they like it. They're getting about 1,000 PSI strength gain. And that's probably because part of it is they're getting a better gap grading. They're filling in for gap grading. And one of the sidebars is, 5 cubic feet of lightweight aggregate. will reduce the weight of that mix 200 pounds. So if you have a 10-yard load, that's 2,000 pounds. Well, that's a half a yard of concrete. And down there, they were running 10.5 yards of concrete out. So they were using 5% less trucks just by doing an internal carrying thing. See, that's common sense. There's no rocket science about this stuff. So how does it wear? Here's a deck that's 34 years old. It was taken out of service because the steel frame underneath it rusted out. The concrete was in almost perfect condition, and you can see the wear was very small. That's right in the traffic lane, and what you're seeing is all this lightweight aggregate, and it's very durable. So you don't have to be afraid about using it as internal curing. Slab warping, they did some studies here, and here's what's very interesting. They said reduce the slab uplift from moisture warping due to the drying at the top and wetting at the bottom. So they've even noticed that it can help you here with warping. And here's a project going down. It's a real test project on a bridge. This is an internal curing project going down in Indiana. It went down just a couple of months ago. There's a lot of other bridges. So I'm getting close here. Internal curing is a common sense approach to sustainable pavements, better hydration, more efficient use of cement and supplementary cementitious materials, reduce cracks and crack width, and it reduces fluid transport, extend your surface life. It improves durability, increases your strength, and there's even more benefits. You can actually get greener concrete because, like everybody wants to do, is more fly ash. Well, let me tell you, the chemical shrinkage of fly ash is twice that of cement, and the chemical shrinkage of slag is 4 times that of cement. So you got to get the water. Judy was talking about how dense these mixes are. You can't get the water in to cure them. If you can bring the water in on the inside, you can make these great mixes even better, a lot better. You get longer service life, lower carbon footprint. You have a better fluctuation with the temperatures, and you get helps offset poor curing, and it can even actually increase the skid resistance. So, can we do it? Yes, we can. We have the knowledge, and we have numerous research reports saying that internal curing extends the surface life. We have solid field data that's pointing all in that direction. And all we need to do is shift our attitudes from 40 years to 100 years. And it's a pretty simple process. The bridge industry did it. They designed 100-year bridges. So I'm going to leave you with this. All great truths begin as blasphemy. And one great truth is, this is the only thing you need to remember. All concrete goes better with internal curing. Thank you very much.
You're welcome. Now, we do have time for questions. Go ahead, sir.
Yeah, in your opinion, is there a minimum absorption you're going to look for in a lightweight? Or are you just going to proportion
It's a proportioning thing. Let's say you get a lightweight aggregate that has a very low percentage of absorption. You probably would need more of that than in an aggregate with a higher absorption, because what you're after is a certain amount of water to hydrate all the cement.
What would you consider low in this case?
7-8%.
Okay.
But see, the other thing is you want to distribute, because you're only getting about 2 millimeters from the aggregate itself. So the smaller aggregates are a lot better because they're distributed throughout the mixture, and therefore you get, you got to come in contact with the cementitious material.
Right. Okay. Thanks.
Thank you.
Well, I'll summarize. I guess if we look at what slide I put up the first, I really think we have addressed all these issues. I think as you can tell, we had great speakers. They were very passionate on what we love. Sustainability is an important part of our jobs, important part of actually our planet. We need to be sustainable in everything we do. And in the people that spoke today, you can see that that is a passion with us. I certainly appreciate everybody that came today. We actually had up to 65 people. At one point, we had a really good session. So for the speakers here, it's really great to see this many people come out and that there's that much interest. We certainly appreciate it. So on that, I guess I thank everybody very much for coming. We really, truly appreciate what you've done and enjoy the rest of the conference. And just a last plug for the conference that's going to be on concrete pavements in Quebec City in 2012. We're looking for people to submit papers and abstracts. So certainly if you have some things on any of the topics of the presenters here today, or anybody that has an idea out there, we'd certainly love to hear from you. And it's going to be in July of 2012, and it's at the Chateau Frontenac, which is one of the nicest hotels in Canada. So, and we're getting really good rates. If you're a government person, you're getting $159 a night, but there's only 50 rooms at that rate. And it's normally over $300 a night, and the other rate for everybody else is $219 or $29. So it's a very good conference, and we're interested in anybody wanting to come and do a presentation. So thank you very much again for coming. And, just one other point. Ternary blends that has been used in Quebec City. They've used them twice, at least 2 times on pavements in Quebec City, and it was very successful. The workability was very good and went down. There was no issues with the placement. So we are moving that way in Canada on going to ternary blends. And quaternary blends actually is one that we're starting to look at now, using cement plus 3 supplementary cementing materials. So thank you very much again.